Welcome to The Explainer. Today, we're unlocking one of the most powerful mathematical tools ever invented. Seriously, it's like a secret key that decodes the hidden structure of pretty much everything around us. We are talking about the Fourier transform.
So let's kick things off with a little mystery. Think about it. The sound of an orchestra, the data streaming to your phone, even the light from a distant star, it all comes at us as this complex, messy signal. How do we even begin to make sense of it? How do we find the simple notes hidden inside that symphony of noise?
Okay, so let's get a good look at what we're actually up against. A signal, like a sound wave or a radio transmission, usually looks like this when you plot it over time. It's just a chaotic jumble, a mess of peaks and valleys that seems totally random. The big question is, how do you decode something that looks like, well, that?
Now, we call this view the time domain, and it's useful for sure. It tells us how strong the signal is at any single moment. But looking at it this way completely hides its true identity, its fundamental ingredients. It's kind of like looking at a cake, but having absolutely no idea what went into it.
So what if we could invent a kind of mathematical prism for these signals? You know how a glass prism takes plain white light and just splits it into a beautiful rainbow of individual colors? Well, what if we had a tool that could do the exact same thing for this messy signal, breaking it down into its pure, simple parts?
Well, guess what? That tool actually exists, and it is precisely what the Fourier transform does. It gives us this incredible shift in perspective. As you can see right here, it takes us from the confusing time domain on the left to the beautifully clear frequency domain on the right. It stops asking, how strong is the signal right now, and starts asking a much more powerful question. What pure frequencies make up this signal overall?
At its heart, the Fourier transform is basically a recipe finder for signals. It analyzes that entire chaotic wave and spits out a simple list of ingredients. And those ingredients are pure, simple sine waves that, when you add them all together, perfectly recreate the original signal. Think of a sine wave as like the purest sound you can imagine, a single note from a tuning fork. The transform tells us exactly which of those pure notes are in there and how much of each one.
Okay, this is where the theory hits the real world. For all the digital signals that run our lives, I'm talking audio files, images, sensor data, we need to adapt this idea. We don't use the original, purely mathematical version of the tool. Instead, we use a specialized version that's built specifically for the digital age. So here's the crucial difference. The original concept, the continuous Fourier transform, it works on these smooth analog waves. But our computers, they don't see smooth waves. They work with discrete data points, little snapshots in time. And for that, we need the discrete Fourier transform, or the DFT. This is the version that lets computers analyze digital audio, process images, and make sense of all our digital data. And this is the mathematical engine that makes it all possible. Now, I know formulas can look intimidating, but what this equation is doing is actually pretty elegant. Just think of it like a machine that is systematically checking the signal for that secret recipe. It methodically goes through a whole range of frequencies, and for each one it asks, okay, how much of this specific frequency is hiding in our signal? This is my favorite part. It is one thing to talk about the theory, but it's something else entirely to see it actually happen. What's so amazing is how just a few lines of code can take this powerful idea and create a genuine aha moment. So let's check it out. It's a really simple four-step process. First, we're going to digitally create a complex signal by just adding two pure sine waves together. Second, we'll look at it in the time domain. And yep, it's going to look like that messy wave from before. Third, we run the DFT. And finally, the magic happens. We reveal the hidden frequencies. And here it is, the brilliant result. Remember that one chaotic wave we started with? After we run the DFT, this is what we get. A beautifully simple chart. Just look at that. Two clean, distinct spikes. One at 50 Hz and another at 120 Hz. That means one wave cycles 50 times per second and the other 120. The DFT perfectly identified the two simple waves we used to create our complex signal. It found the recipe.
So why is this so important? I mean, who cares about finding this recipe? Well, it turns out that knowing a signal's ingredients gives you something like a superpower. Because once you know the frequency recipe, you can start changing it. In audio, you can boost the bass or get rid of a high-pitched whine. That's basically what noise cancellation is. And think about data compression. Formats like MP3s and JPEGs,
They work by using the Fourier transform to identify and just toss out the frequency information our ears and eyes are least likely to notice. That's how they make files so much smaller. It is absolutely fundamental to how our digital world works.
So the classical Fourier transform that we've been talking about literally built our modern digital world. But you know what? The story does not end here. The core principles of finding a signal's hidden recipe are now paving the way for the next frontier, a true quantum leap in computation.
As powerful as the DFT is, it does have its limits. When you're dealing with truly massive data sets, we're talking the kind you see in drug discovery or complex financial modeling, even the most efficient classical versions can get incredibly slow.
And that is exactly why grasping the DFT is so essential today. It is the foundational first step to understanding the quantum Fourier transform, or QFT. The QFT is a key algorithm in quantum computing that promises to do this same recipe-finding trick, but on an exponential scale, solving problems that are just impossible for classical computers today.
And this leaves us with a final, really fascinating question to think about. The classical Fourier transform gave us MP3s, JPEGs, and noise-canceling headphones. It gave us our digital world. So what new world is going to be built on the back of its quantum counterpart?